All right. So today we're going to continue and finish chi-square tests, and we are also going to finish the linear regression because it's only one section in chapter 11. Probably we're going to start chapter 5 next week. Let me quickly recap what we have did last time on Tuesday. So chi-square tests are used to conduct a test to three different things. First, we have a sample and we want to test whether this sample is coming from a specific distribution. This may be, for example, testing whether a pair of dice is fair or not, or the grades in course are randomly distributed or not, things like that. So we can test against a discrete distribution or a uniform distribution or any specific distribution. So we can test, for example, whether a sample is coming from a normal distribution with mean, for example, 50 and standard deviation 2. So that's the specific distribution part. So that's 10, 1, 1. So the first part, if you look at the table of contents of this chapter, so I'm recording right here. Testing a distribution is talking about the specific distribution where we're testing against a distribution with known parameters. Okay, like if we're testing against Poisson, this means that we're testing a Poisson with specific lambda. The second part, testing a family of distribution, is just saying that if we don't know the distribution parameters, but we want to just know whether this sample is coming from Poisson or not. In that case, we also estimate the Poisson parameter, lambda, or if it's, for example, we're testing again, if this is the sample normally distributed, the sample is coming from normal distribution, then in that case, we have to estimate both the mean and standard deviation by using two estimates for them. So when we are testing against a family of distribution, we first estimate it by using maximum likelihood. The parameters are estimated. Then, just like we did in the first part, testing against a specific distribution, we do the exact same test. The only difference is that because we estimate these additional parameters, this decreases the degree of freedom we have in chi-square tests. So the chi-square distribution, the only parameter, the PDF of chi-square, which is shown in the previous chapter in the section that we skipped. So this is the chi-square distribution. So the only parameter it has is this degree of freedom. So this V is for degree of freedom. And as you can see, as the degree of freedom changes, as it increases, this looks more and more like normal distributed, but with smaller degrees of freedom, it's a more right-skewed distribution. All right, so the chi-square test that we perform, it's always a right tail test, and our null hypothesis is that when we are testing against that specific distribution, our null hypothesis is that the sample is coming from that distribution. Okay, for example, if we are testing whether the dice is a fair or not, we assume it is fair, and our null distribution is the case where it's fair. We know all the probabilities are equally likely. And the last thing is testing independence, whether when we have two random variables, we may use chi-square test to see whether they're independent or not, again with some significance level alpha, or we can get a p-value after this test, and based on that p-value, we can say the sample shows significant evidence that these are not independent, or the sample do not have any significant evidence that these are not independent. So it means that you may assume that they are independent. So here the null distribution will be that they are independent. Okay, again, it will be some equality. Assuming that these two random variables are independent, we are going to form our expected values of those chi-square bins. and then we are going to compute the chi-square statistic. I'm going to solve some examples about these today. And also, again, just like I did in chapter 9, I also have a recording of 3 exercises, solution of 3 exercises that I did last year. I'm also going to put that on YouTube in our playlist, and you will also have a chance to experience more exercises at the end of this chapter 10 about this section. All right, so I will upload them today with today's lectures. So chi-square statistic is always a positive statistic. It's basically, its formula is very simple. We just take square differences between some expected counts. So these are all counts, but they may be not integers. They may be floating point numbers. When this count, for example, is if the probability to observe something in that bin is, for example, 0.002, and you have, for example, 100, or depending on the number of tries that you have in your sample size, the expected value here could be non-integer values like 5.2 or 12.3. But the observed counts will always be integers, because your sample your sample has some data points, and when you partition your domain into regions, into bins, they will be mutually exclusive. So a certain subset of your sample is going to fall into that bin, and they will always be integer counts. So the observed counts are always integers, but these may not necessarily be integer. But as you can see, what we do is we take the square difference in order to have it show the deviation, the distance from it. If we don't take the square, it may sometimes have a negative contribution, sometimes positive. So at the end, we may not know whether really it's far away. That's why we take the square, so it becomes positive square distance from the expected count. So the larger this is, it means that we have more evidence that the observations are not coming from. So if there's big difference between observation and expected one, it means that there's large evidence that the observed values are not coming from the null distribution, the expected ones. But if the observed ones are similar to the expected ones, and then it means that your null distribution may be true. There is no significant evidence. The chi-square value will be small in this case, and there will be no significant evidence against the null distribution. And these values, these square distances, are normalized by the expected counts to just have equal contribution from each of those bins. So therefore, they are normalized like this, and they're summed up. So it's a summation of differences. On Tuesday, we talked about the first 2 examples. If we quickly go over them, for example, testing whether a single die, or this is the single die is fair or not. So a gambler in 90 tosses of a die, these were the observed counts. As you can see, very few compared to ones, which came 20 ones. There are only 9 fives, so which means that it's like 1 comes 2 times more than 5. Okay, but is this significant evidence? In 90 sample, in a sample size of 90, is this significant evidence that this die is not fair? So if it can we observe the same thing? Because since it's a sample, there are going to be, we don't always expect them to be 15, 15, 15, 15, right? There may be, due to chance, there may be differences. So is this difference, is this deviation from 15s here are significant enough to claim that the die is not fair? So again, we can do this hypothesis test. So this is our null hypothesis, is that the die is fair. Alternative hypothesis is not fair. It's not equality here. But as you stated on Tuesday, when we don't have equality, why don't we conduct 2-tailed tests? Because chi-square, we always look large deviation, in order for favor of alternative hypothesis, the chi-square statistics should be large. For small values of chi-square statistic, we favor the null hypothesis. Therefore, it's always a right tail test where only large values of the chi-square statistic will be considered as significant enough evidence against the null hypothesis. Therefore, this not equality in this case, it's always a right tail test. So here, so we conduct a hypothesis test basically. If it was fair, it would be uniform discrete distribution here with 1/6 for every die number. And these are the observed counts. The expected counts will be 90 times 1/6. So it's like a binomial distribution. We are going to compute the expected counts similar to that. Sometimes we may also, actually, we're going to compute the expected counts. Always the sample size always has to come into picture. Sometimes this probability to be in that bin may be found by taking the difference of two CDF values. If it's what I'm trying to say is that if we have a continuous distribution like this, imagine we have a continuous distribution that is like this. Okay, so it may be bimodal. There may be multiple modes of this. This distribution does not look like a normal distribution, but imagine we have some arbitrary distribution that is like this, and we may divide this distribution into bins. Bin number 1, bin number 2, bin number 3. This is 2, number 3, number 4, and number 5. So we may partition the domain into 5 regions like this in order to perform our chi-square test. In that case, for example, if the sample size is equal to 200, for example, we would like to know in these 200 samples, what is the expected count of number of data points, for example, that fall into bin 3. How do you figure that out? The probability to fall in bin 3 will be equal to the area under the curve, right? Which is equal to whatever these thresholds are as you find your bin boundaries. This is from -infinity to this value. This is between these two values. So after you have your bin boundaries, the probability for a random x to be in bin number 3 will be the probability, the CDF value of this one minus the CDF value of this one, which gives you the area under the curve here. So after you find the area of the curve on here, that's your probability, and you multiply with this n, 200, to find the expected count of numbers that fall in this bin 3. So we will have to always consider the sample size to determine the expected counts. But when we're finding these expected counts, sometimes they may be discrete probabilities like this example. 1/6, the probability to obtain 3 in a fair dice is 1/6. So the expected count is 15 when you have nitidoses. All of them will be 15 in nitidoses. But depending on the distribution, we may have to compute that probability that will replace this 1/6 differently, and again have to multiply that with the sample size to find the expected count. And here the chi-square statistic, when we look at the square differences and normalize everything by 15, it turns out to be 5.2. So I did this load the package beforehand. So 5.2 is our value. When we degree of freedom in this case, there are 6 bins. When we are testing against a specific distribution, the number of bins, the number of regions we have -1 becomes the chi-square degree of freedom, and -1 becomes the degree of freedom. So with 5 degrees of freedom, the value of 5.2, if you look at the table in the appendix, appendix A6, it says it falls in between 0.2 and 0.8. And if you do octave online to find the exact value, the value of x, degree of freedom 5, it's 0.39. So the p-value is really high here. Only with p-values, for example, less than 0.05, we can say that there's significant evidence against the null distribution. So since the p-value is rather high here, it means that there is no significant evidence. Our sample, this one, does not show significant evidence against the null distribution, which says it's fair. So the die can be fair, and we can obtain these results with some probability. Okay. So, or we can also say that since this is alpha with significance level 0.39 or less. I mean, if your significance level alpha was 0.4, okay, when alpha is equal to 0.4, if alpha was equal to 0.4, then we would say that, oh, okay, this die is not fair because the rejection region will be that. I mean, when we get a p-value less than this, we will reject it. But nobody uses a significance level of 0.4. It's like, you mean you're 60% confident that the die is fair. So alpha, remember, is 1 minus alpha is your confidence. So which is 1 over 1 minus 0.4, 0.6. You don't conduct a hypothesis test with just 60% confidence. That's too low. So therefore, this is, in most cases, when the p-value is larger than 0.1 or even 0.05, we say that the evidence is not significant enough. And therefore, we accept the null hypothesis, in which the die is fair. And the only difference when we are testing against the family of distribution is we first estimate the parameter. And the example we have looked about here was example 10.2, where we first estimated lambda to be 1.55. And then since it has only one parameter, Poisson has only one parameter, lambda, what this will do is it's going to decrease our degree of freedom when we conduct the test. So after this point, after you find your lambda with maximum likelihood, the only difference from the test that we performed in the previous subsection is that the degree of freedom is decreased by the number of parameters, which is 1 here, and we use this as our lambda. And here, this example was also interesting in the sense that we have, although it's a discrete distribution, its domain is infinite, which means that it starts at 0, 1, 2, and goes all the way to infinity. And therefore, when we are deciding on these bins, if this is, for example, Poisson, so we are going to have a probability mass function. Maybe it's going, I don't know, maybe it's going to be something like this. If you look at the probability mass function, we have to decide, when we decide on bins, we may first decide 0 to be its own bin, but we have to decide from which, for example, is this going to be from 4 to infinity or 5 to infinity? The important thing here is that the expected counts in a bin should be greater than 5. That's another rule of thumb that we use. Two things are needed when we're performing chi-square test. The number of bins that, when we're doing the partitioning, we don't want the partition to only small number of bins. They have to be at least 5. The number of bins have to be at least 5 to have some. Otherwise, your degree of freedom is going to be very low, right? You don't want your degree of freedom to be very low. You want with high degrees of the higher the degrees of freedom, the more you'll be able to find some significance. Because with low degrees of freedom, your confidence will be, I mean, the chi-square distribution, as you can see, it's really very close values. You have to, your test will not be really accurate when you have small number of bins. So in order to have a more accurate chi-square test, the number of bins has to be at least 5, and also the expected values that fall into these bins, the expected counts that fall into these bins should at least be 5. So these are two things. So when the first case where we decide to have the bins is 5 all the way to the infinity, when we see that the expected value in this case is only 3.6, because the probability to have 5 or more transmission errors in this Poisson distribution where lambda is 1.55 is a very small probability, 0.02. So if you multiply 0.02 with, what was our sample size? 170. If you multiply 170 with this, it's only 3.6, which is less than 5. So what we can do is, so these were 6 bins here. We can decrease the number of bins to 5 by merging the last two. And this is exactly what is done here. They are added up, and the last bin is from 4 to infinity. And these are the expected counts. All of the expected counts are larger than 5. The observed counts, another important thing here is that the observed counts themselves may be less than 5. There's no rule of thumb, or when deciding the bins, we don't need to consider the observed counts. The observed counts in a bin can be less than 5. Okay, that's perfectly fine. So in this case, the expected counts, all of them are greater than 5. We again find our chi-square statistic. This time our degree of freedom is even less, 3 degrees of freedom. And this time the p-value is between 0.1 and 0.2, although it's smaller than in the smaller compared to the previous example, it's still not significant enough. So 0.1, if the p-value is larger than 0.1, we most of the time consider it as non-significant. So there's no evidence against the Poisson distribution for these transmission errors. One thing that is interesting I want to mention here is that I think it was one of the exercises that I solved that I'm going to upload in that video. We may conduct for the same sample, we may also test whether it comes from normal distribution. Okay, how would we do that? For example, for the same example, we could have actually so the thing is that normal distribution actually is continuous, but assume that continuous, we may be looking at average transmission errors between intervals, but so if we can test this against some normal distribution too, with some mean and standard deviation. And the only thing that I want to say here is that, I mean, even if we are comparing it again, another discrete distribution, the result may be that the sample may belong to Poisson and the sample may belong to the other distribution too, which may seem a little bit contradiction at first. So what I'm saying is that when we conduct these tests, we may have no evidence against Poisson, significant evidence, and we may have no evidence when we conduct the test to test again to test whether it comes from another distribution. And it may be, the result may also come as the result may be there's no significant evidence against that distribution too. So the sample may be coming from this or that. And as I said, although this seems like contradiction, it's not. I mean, since due to sampling errors, we're just saying that it may be Poisson or it may be this something else. I mean, the distribution, the sample here does not deviate enough from either of them. So whether you treat it as Poisson or you treat it as this normal distribution does not make any difference. You may treat them whatever you like, because the sample looks like both of them. There is no evidence against either of them. This may be the case. So in one of the examples that I solve in the video, there will be, I think, the test against two different distributions. And in both of them, we will probably accept the null hypothesis. But this doesn't mean, I mean, we may be doing, since we are conducting these tests with certain error probabilities, one of them is the true thing actually, the other is wrong. So it's coming from some distribution, but our sample does not provide significant evidence against neither of them. So that may be the case. And oh, I think this is that one. can we assume, so this is another example, the network load, whether it's coming from normal distribution or not. Here, we have an example in which we have to estimate two parameters, both mu and standard deviation. So this is referring to an exercise on chapter 8.2. We first find sample standard deviation, sample mean and sample standard deviation is used as the best maximum likelihood estimates of mean and standard deviation. So, so two parameters are estimated. Again, we have our bins this time. Both the first bin and last bin extends all the way to infinity because it's the normal distribution, and we have 6 bins here. If you look at the expected counts, they are all greater than or equal to 5. So I wrote in my here expected value greater than 5, but it may be 5. You can say greater than or equal to 5 here. So when it's 5, it doesn't matter. You can still conduct the test. And these are the observed counts from that table. When we find that the chi-square statistic is rather small here, 1.07, so it may be coming. So again, there's no evidence against the normal distribution, so they may come from normal distribution. We can also use method of moments to estimate in chi-square, but I think it's most of the time maximum likelihood is used. But yeah, when you're estimating these parameters, I don't think there's a hard rule against using method of moments to estimate the parameters. You can use them. In the question, probably it will be specified to you use maximum likelihood, or unless otherwise specified, you can always use maximum likelihood. And in some of these estimates that we have seen at the beginning of chapter 9, we have seen that both methods, method of moments and method of maximum likelihood, their estimate, the formulas are the same in some cases, so it doesn't matter whether you use that or that. But so there is no, I don't know for sure that in chi-square test, it's a written rule, hard written rule that you have to use maximum likelihood. But in most of the cases, I think it's a bit good approximation, good estimation to the real parameters. So that's maybe the most widely used method to estimate these parameters. But yeah, I think you could use method of moments. So yeah, and the final thing that we're going to cover from this chapter 9 is testing independence. So this is also nice because this comes up a lot in, for example, machine learning, where you have features that you collect, for example, the weight and the length of certain things, or is the color dependent on some other parameter. For example, you're looking at trees, and the tree trunks may have some colors, and you also collect age of those trees. You also know the ages of those trees. For example, the color of the tree trunk, is it correlated with, you may compute color with some kind of a quantitative value, like a different shades of brown. And where you may want to know whether it correlates with age of the tree. So these kinds of things, whether two parameters, two features that you two quantitative features that are correlated or not, comes up a lot to figure out whether two parameters are related or not. So here, our null hypothesis will be that they are independent, and our alternative hypothesis will be that they are dependent. Okay, so we are going to divide both the domain of A and B, whatever these random variables are. These random variables may take values from different ranges. We are going to divide those ranges again into bins. And since we're dividing the ranges of A and ranges of B into bins separately, we will actually have a table of values of A and values of B. Okay, just like in chapter 3 in discrete distributions, where we were thinking about joint distributions, where we had a table that shows, for example, a random variable x against a random variable y, where we had this table that shows for different values of x and for different values of y. Just like that, we are going to divide the values a and b can take into these regions, which will give us a table. And I think it will be understood best with the example. But what will so this is this table. This is also called the contingency table. K, the values of A is divided into K different values, K different regions. The values B can take is divided into M different regions. So we have an M times K table. And what we're going to, so this is N is our total number of samples. Each of these table cells, they will show some mutually exclusive event, and their summation are exhaustive. They are all of our sample. And for example, if this N21 is the count of, if these are for observed counts, it will be the count of sample data points which are in this A2 bin and B2 bin compared to when we look at the features in A and features in B. And these numbers, so we have M times K values here. We are going to also have expected counts. And you may assume that the expected, you may actually understand how the expected counts are going to be found, right? If you look at this, the probability, by looking at just the counts of A, the probability to have, to be in the first row, to here, is going to be N1 dot divided by N. So each of these rows at the row counts at the end is also going to give us probabilities. The probability to have this value of A1. So actually we are estimating these proportions again from our samples. So these are therefore some things that are estimated. So, if we assume independence, the number of expected count here will be equal to, so let me write it here. So it's actually very, very simple. So here it's like this. So when we look at the proportions, for example, if 0.2 of the A values are here in this first row, okay, and if, for example, 0.3 of the total samples are in this B1 row, if we do the column sum, okay, if they were independent, we would expect the probability to be A1, A is equal to A1, and B is equal to B1. If they were independent, it would be the multiplication of these two probabilities, right? It will be 0.06. So this will be our probability expected, it will be probability under the null hypothesis to have, to fall into this table cell. And when we multiply this with our sample size, we find our expected count to be in this table. And if obviously N11, the observed count, is likely to be different. Even if they're really independent, since it's just a sample that we have, there are sampling errors, and the actual N11 count can be different than what we have here expected. So we are going to find the differences of these, probabilities here of these cells are going to be found out by multiplying these probabilities, assuming they're independent, and then multiplying these multiplied probabilities on their independence with our sample size to find the expected counts. And that's it. And at the end, our degree of freedom will be M times K minus 2. Here M is the number of columns, N is K is the number of rows. That minus 2 will be our degree of freedom when we conduct this test. So let's see. Yeah, we have M, K values. We compute the chi-square statistics as usual by computing the difference of each of the observed count in a table cell against the expected counts. And as you can see, the expected counts are found by multiplying those probabilities, probability of to be in that row, probability of being in that column. This is under null hypothesis. If they were independent, this will be the probability to be in that table cell ij. We multiply that with sample size to find our expected counts. And the degree of freedom here becomes k minus 1 times m minus 1. Actually, I wrote it incorrectly. I just called plus, right? So it's not true. So it's going to be m minus 1 multiplied, because the number of cells here is m times k, but each of them, if you look at the degree of freedom, it will be m minus 1, k minus 1 here, times k minus 1. Yeah. So let's get back to here, how it's computed. So it's the detail here, how the degree of freedom is computed. So we have this many linearly independent constraints, and degree of freedom therefore becomes this one. The number of parameters that are estimated, how many of them are independent. So this number, k times m minus k plus m minus 1, gives us simply a k minus 1 times m minus 1. So here's the summary for that testing for independence. We first divide both random variables into regions. We compute, just count the observed counts that fall into those table cells. And then we compute the expected counts, and with k minus 1, m minus 1 degree of freedom, we conduct a test. And let's look at this example at 10.4, and this will actually conclude chapter 10 after we finish this example. So here it's the relationship between a mail being spam and its attachments. We're just looking at image attachments, whether it has image attachments or not. So we collect 1,000 emails. So 1,000 emails are collected, and here are the statistics that we have about these 1,000 emails. There are actually 400 of them are spam emails, 600 of them are not spam emails. So this is like our this data is given to us knowing that this is like training data that we already know. 400 of them are spam, 600 of them are not spam. So out of those 400 spam emails, 160 have images, 240 have no images. And from among the no spam emails, this value is 140 with image, 460 no images. So if you look at the total number of emails with images were 300, and the total number of emails with no images 700. So the probability, I mean, these two random variables, the probability of an email to have an image attachment or not, the probability that it has image attachment is 0.3. The probability that it has no image attachment, regardless of whether it's spam or not, it's 0.7. And being spam is like 0.4. Being no spam is 0.6. So these are our individual, these are our independents, just probabilities for those. Now, the probability, if they were independent, the probability to be spam and contain an image would be 0.3 times 0.4, which is 0.12. So that 0.12 multiplied by 1,000 gives you 120. And here, in this case, the number of bins we have actually is just 4. But we cannot increase the number of bins, right? I mean, because our variables that we are looking at are just like Bernoulli variables. They have binary values, with or images or no images. There's no in between. If it was, for example, if we collected data which shows how many images it contained as attachment, 0, 1, 2, 3, then we would have more table cells. It's like the total number of chi-square bins is 4 in this case, but we cannot do better than this. We will have to live with 4 chi-square bins because both of these variables, they're just binary, with or no image, spam or no spam. So these are our four values, and these are the expected counts under the assumption that the null hypothesis is true when they are independent. If they were independent, these would be their real counts. So let's compute the chi-square statistic by looking at the differences between observed counts and the expected counts and normalizing everything with the expected counts, as you can see. And the chi-square statistics turns out to be 31.75, even in this normalized version. This normalization is really good, as you can see. Whether this number is large is not, it's not large because we have our sample size is really large and we have many images. It's large because we do normalization with respect to expected counts. So everything we get here are some normalized values. It's large because probably it's really, they're probably not independent. We may have significant evidence against that null hypothesis that says that they're independent. So with 1 degree of freedom, as you can see, the degree of freedom is really small. So it may not be, we may not be very confident against this test actually, because it's a very low degree of freedom test. But we find that the p-value of this large chi-square statistic is, which is 31.75, it's even less than 0.001. So we can actually consider that it's significant enough evidence. We have significant evidence that an email having an attachment is related to being spam. So actually, I'm not so sure about whether this low degree of freedom is, again, you need to have some caution against, because, I mean, the book doesn't say anything about, I mean, because it doesn't interpret this low degree of freedom being something bad. So it may not be bad, okay? So what I'm saying may not be totally correct. So just ignore my discussion on degree of freedom. Maybe we just use however we are supposed to compute the degree of freedom given in the question. But intuitively, I would expect chi-square statistic to be more reliable if we have a higher degree of freedom, right? But as I said, the book does not discuss this. Maybe I may be wrong about this intuition that we need higher degrees of chi-square statistic. But this intuition is also in parallel with, if in the first part of two tests we conducted in the first two subsections, testing against a family of distributions or testing against a specific distribution, the requirement that the number of bins have to be at least 5, it has to do something with trying to have higher degrees of freedom, right? So it may have some merit in trying to get higher degrees of freedom for more reliable chi-square tests. And so this one is an example where we have many columns and 3 rows here. So the degree of freedom here, this case would be 1, 2, 3, 4, 5, 6, 7. 6 times 2, 12. So degrees of freedom here will be 12. Again, we do the exact same thing. We just compute the probabilities by dividing each of these numbers by the total number, probability to be no purchase, single purchase, or multiple purchase, and multiply these probabilities and multiply them with the sample size to find the expected counts. These are our expected counts. These were observed counts. Compute the chi-square statistic. It turns out that they are, it's again a very large number. Look at the 60.79. So with 12 degrees of freedom, p-value is really a small number here. Again, we have significant evidence that they're not independent. Significant evidence against being independent. So they are probably dependent. So there's significant evidence that the probability of making a single purchase or multiple purchases varies during the week. We compute this not norm CDF, we compute it with chi-square. We look at the chi-square statistics. Let's take a look at this, for example, 6.79. We actually conduct exactly this. Let me connect here. 1 minus chi-square CDF. What was it? 60.79? Was it like that? Let me take a look at it. Yeah, 60.79. and we also have the degree of freedom 12. We conduct this one to compute the chi-square statistics. So chi-square CDF. Wow. So I need to load the statistics since I disconnected. So yeah, it's really small. As you can see, it's even smaller than 0.00001. So we after we compute the chi-square statistics, we don't use norm CDF. In all the tests we perform, the chi-square test that we perform in chapter 9 here, 10 here, like testing independence, testing against the family of distribution, we always use the chi-square distribution, chi-square CDF with degrees of freedom, and the chi-square test statistics that is computed by looking at the differences between these two things. Because the value that is we compute here is not normally distributed. This is not normal distribution because it can never get negative values. It's always positive. But it may be normal approximation could be used maybe to compute larger values of when the degrees of freedom gets larger. As you have seen, it's more like symmetric two-tailed distribution. It may be, but it's not infinite tail on the left-hand side. It always ends at 0. Exactly, we use that 1 minus thing because it's the right tail distribution. So if we do this like this, the area under the curve to the right-hand side, because this chi-square, if we do it like this, it gives the area of acceptance to us, because 6.79 was our value that we computed as the chi-square. So the area to the left of it is our CDF, and it's, as you can see, it can't even compute. It's like answer is 1.0. Actually, it's 1.0000 something. I'm sorry, 0.99999 something. It's a very number very close to 1.0. So this is like the acceptance region. I mean, the area, our chi-square statistic is that extreme, that different from what would be expected. Yeah, it's also when we were conducting z-test. In z-test, we were using 1 minus norm CDF. So z-test, when you're testing, for example, against the mean of a population, 1 minus norm CDF for z statistic, when we have to find the p-value again, when we conduct a right tail t-test again. If it's a one tail, the p-value could be again only if it's a right tail test. 1 minus norm CDF will give you the p-value. So again, let's take a look at that. In the case of a z-test, the p-value could be actually, and after that we're going to have our break. So if it was a z-test against normal distribution, if it's a two-tail test, the p-value actually could be on both sides. So what we may need to do is, after we perform this, we may need to divide whatever the value we have here, we may need to divide it by 2 because this area, or actually in that case multiply by 2, right? I mean, but if you have a one tail, a right tail t-test, 1 minus norm CDF will immediately give you the area under the curve here. So how likely a random value is going to contain a random value from the null distribution? Remember, this normal distribution is always showing the null distribution. How likely a random value from the null distribution can get a statistic more extreme than what we have obtained? That's the area under the curve here. When we say more extreme, if we are conducting a two-tail test, this may also be considered as more extreme. Then in this case, we will have to sum up these two areas to find the p-value. But if it's a right tail test, we will be looking more extreme. Being more extreme, will be just looking at this side here, and it will be just 1 minus norm CDF. Here, our sample being more extreme in the chi-squared statistic is that they are really dependent on each other. So they're very far away from independence. It means that they're very this chi-square statistic is really a large number. So this 60 was a really large number, and the probability, the p-value, the probability to obtain a more extreme value under the assumption of null hypothesis is really, really, really small, as you can see here. Therefore, we reject null hypothesis in favor of the alternative hypothesis, which alternative hypothesis tells that they're dependent. So they're most likely dependent. Okay, so this concludes. There are some MATLAB code to show you a demo to show how chi-square tests for independence. You can do that in MATLAB if you have a large table like this. Computing all these things by hand may be cumbersome. So what you may do is if you have an array of things, you can actually just compute your table. So here, this is actually a table, I think. Two values, hundreds. So this is for that spam example, right? With 700, oh no, so a total of 1000 emails. I think they add up to 1000. So if this is our table, these row sums, column sums, the total ones, we just, this is how we can compute the probabilities to have attachment or not, to be spam or not. And then for all table values, we compute the expected values. The chi-square statistic then becomes the summation of these differences, and we compute the p-value like this. So this is just a small code snippet that you can use to do these things, and you can write also a C code to do that, right? You don't need to use MATLAB. It's really simple. All right, so this concludes our discussion on chapter 10, and let's have a 10-minute break now, and I will see you all at 10:43. I will stop recording now.